In lesson 1.4, we're going to look at the arc length and sector area of circles. So on the left, we have a circle with radius 3 centimeters. And if we wanted to calculate the circumference of this circle, we could use the formula 2 times pi times the radius. But since we know the radius to be 3, we could do 2 times pi times 3, which is going to give us 6 pi centimeters, is the circumference of our circle. If we wanted to calculate the area of the circle, we could use the formula pi times the radius squared, but we know the radius to be 3, so we could do pi times 3 squared, which would give us 9 pi square centimeters, or centimeters squared. Okay, and what I want you to note here is that the radius of the circle is the key. Okay, the radius of the circle allows us to get the circumference, the area, and sort of figure out anything that we like. So I like to say that the radius of the circle is the key. And here's a little key, and that's the radius. Okay, very good. So now we want to talk about sector area and arc length. So if I make another copy of this circle, okay, and I give it the same radius of 3 centimeters. But this time, let's say I have some angle theta, and let's call it 120 degrees. And I put a point A and B. And let's say I want to know how long is this arc? What is the arc length of AB? So if I want to know the arc length of AB, well, the arc length is a part of the total circumference. So it is some fraction of the total circumference. And we know what fraction it is because we know the angle is 120 degrees out of 360 total degrees. And then we multiply that by our circumference, which is 6 pi. And that gives us that the arc length of AB is going to be 2 pi centimeters. Okay, so this length is 2 pi centimeters. All the way around is 6 pi centimeters. Great. We can also find the area, the space inside this sector, which I'm going to just call the sector area. I'm going to name this center point M, so I can say the sector area of this sector MAB. Again, it's going to be equal to this fraction, 1/3, or 120 out of 360, times the total area, which in this case is 9 pi. So 1/3 times 9 pi is going to give us 3 pi centimeters squared, meaning that in all this, there are 3 pi square centimeters of space. Okay, so that should be a little bit of a review from geometry. But the really important thing that I want you to take away, and that all the math is based around, right? Like you can use a formula, or you can set all this up, but the really key understanding is that sector area and arc length are fractions. And by fractions, I sort of also just mean like portions of the total area and total circumference. So everything that you need to do mathematically comes from this fact, and all the math, any formula, any sort of equation that you're going to build comes from this fact. And if you understand that, this should be pretty easy. And if not, you should work to understand that. Okay, so using this fact, I want to show you one of the reasons radians can be kind of nice. So let's draw another circle. And this time, let us say that the circle has an angle measured in radians, and let's call theta 1 radian. Okay. And now radians are unitless. I don't need to write radian, but I'm just going to sort of help you out. And our radius, let's still say, is 3 centimeters. Let's name this point M, this point A, and this point B. So the first thing is, if I want to find the, let's do arc length. If I want to find the arc length of AB, it is, recall, a fraction of the total circumference. Okay, so the fraction. We would find the fraction because in radians, we know there are 2 pi radians all the way around the circle, about 6.28 of them. And our angle that we're working with, the portion of the circle that we have, is 1 radian. So our fraction is going to be 1 radian out of 2 pi radians, or 1 out of 2 pi. And then our circumference of the circle, we said, was 2 pi times the radius, 3. And now here's the part that's really nice about radians. The circumference is 2 times pi times the radius, and we have 2 pi radians in the whole circle, so these just cancel, giving us 1 times 3, which is just 3 centimeters. And that's always going to happen because radians are defined sort of as how many radiuses or radii you can wrap around the circumference. So like if I took this radius of 3 centimeters, 1 radian literally means take that, wrap it around the circle, and where you get is 1 radian. So like there's 3 centimeters. Do it 2 pi times and you'll end up all the way around the whole circle. So we kind of end up with this idea for arc length, where arc length, so long as we're doing it in radians, is equal to the radius times theta. And this is only if theta is in radians. Okay, now, if you understand that, cool. I'm going to say you are not allowed to use this formula, okay, unless you really, really, really understand that. I would really prefer you go through this motion because that's the main idea here and what I want you to understand. I'm showing you this because this is just illustrating like the power of radians and how radians can make things a little bit easier, like arc length being r theta, versus if we're in degrees, you have to do theta over 360 times 2 times pi times r. Let me put that here. So it makes that conversion between an angle and let's put this as degrees. Okay, makes the conversion between angles and lengths much easier, which is one of the things I said way back when we introduced what radians could be good for. But I really don't want you to do that unless you really, really understand it. I just want to show you that like if you start doing physics and all these like things where you have to do arc lengths all the time, like, yeah, radians are awesome, but it's not going to really help develop your math understanding to just use that formula. Okay, let's take a look at the sector area then. So if I want to calculate the sector area of this sector MAB, and if I highlight that, I'm talking about all this. Well, it's a fraction of in this case, a fraction of the total area. So the fraction is the same. It's 1 radian out of 2 pi radians, right? Because it's 1 radian of angle out of 2 pi possible angle, one way around the circle, and then times pi times r squared. And in this case, radius is 3, so I can fill in 3 for the radius. Now notice the pi's cancel. That's pretty nice. So we're left with 1 over 2 times 9, which is just 9 halves. And that should be centimeters squared because it's an area. So again, this is a little nice, and it's not totally obvious, but no matter what, whatever our radians are, we're going to end up dividing by 2 and then multiplying by the radius squared. And I really don't want you to use that one. But the sector area, when we're using a theta in radians, we can do theta divided by 2 times r squared. And let's make that consistent color scheme here. Okay, where theta is in radians. Comparing this to when theta is in degrees, we end up with theta over 360 times pi times r squared. You can see this is a little bit cleaner. Like we don't have any pi, we don't have a 360. So again, I'm just illustrating the power of radians. but I really don't want you to use that. What I want you to have, and what I will ask in some form on the test, you need to understand the main idea that the arc length and sector area are fractions, so I'll write it out. The arc length is a fraction of the circumference, and the sector area is a fraction of the total area. Okay. Or a portion, or whatever word you want to use. So that's how I want you to use this. On the test, I'm going to ask you a question that's going to try to make you use that understanding that will be less useful if you just know the formulas. But I did want to show you that because eventually, like if you're doing all this physics and stuff, like it's handy to use formulas that are easier to work with. So hope you enjoyed this video. Hope it's a good refresher on sector and arc length. Thank you for watching.